Bienvenidos a nuestra transmisión del Comité de Investigación de la Asociación Mexicana de Geofísicos de Exploración. En esta ocasión, con Geofísica más allá de los hidrocarburos, venimos con la presentación del doctor John N. Louie, titulada Surface Wave Surface Building a Community Seismic Velocity Model for Nevada, USA, for Physics-Based 3D Earthquake Ground Motion Prediction. Le voy a ceder el micrófono al doctor Sergio Chávez Pérez para que nos dé los generales del doctor John y poder continuar con nuestra charla, que suena bastante interesante para el día de hoy. Gracias por estar presentes.
Buenas tardes. Ya que están viendo la pantalla, por ahí abajo del título aparece algo que dice Louie.pv. Ahí pueden encontrar el material biográfico, laboral, publicaciones, muchas cosas que John ha realizado y sigue realizando. Muy en breve, John terminó su doctorado en 1987 en Caltech, en Estados Unidos. Ese mismo año se fue a la Universidad de Penn State como profesor asistente. Posteriormente, en 1992, se fue a la Universidad de Nevada en Reno, donde permanece hasta el momento y es profesor en esa área, en particular en el laboratorio sismológico. Él actualmente está de sabático hasta agosto del año próximo y tenemos la enorme fortuna de contar con él. Él me hizo notar que le gustaría que mencione que aun cuando él creció, se desarrolló y estableció su nombre en representación sísmica, que es la traducción que algunos optamos para Seismic Imaging, actualmente se dedica más a aspectos de riesgo sísmico, lo que en México tendemos a referirnos como ingeniería sísmica o ingeniería sismológica, y que también es una combinación de sismología de exploración y de terremotos. Pero comentando antes de esta introducción, él decía que una buena definición es que actualmente se considera un geofísico geotecnista. Reiteramos el privilegio de tenerlo con nosotros y adelante, John. Go ahead, John.
Thank you very much for the invitation, and I am honored to be presenting in front of your section of the SEG. I want to acknowledge that I work in an area that used to be Mexico and is still inhabited by the indigenous peoples. And they have never relinquished their claim to our lands. So I'm going to talk about the application of essentially seismic imaging wave field concepts to the protection of Nevada's economy and population from the effects of earthquakes by trying to anticipate earthquake shaking when the earthquake does occur. Along the way, we're going to see that there is a need not just for predicting earthquake shaking, but also from the construction and civil engineering fields for geophysical surveys. Now, all of this work is really a collaboration with my students and certain colleagues like Dr. Ken Smith of the Nevada Seismological Laboratory. But my recent master's graduate, Eric Eckert, my recent PhD graduate, Michelle Scalise, and two undergraduate interns who I think you should be very interested to follow where their careers go, because they're very smart, very capable, Alex Simpson and Jacob Ortega. These students really have done almost all of the work here, along with other colleagues I'll talk about. And I'm just representing them to you. All of this work is described in some way, a whole variety of papers and reports at my website, as Sergio told you, louie.pub. And in particular, there's a Zenodo publication of the surface wave survey archive. Now, what is the reason why I think that we are going to have, I believe, a revolution in geotechnical geophysics? We are going to be still doing oil and gas seismic imaging for some time. We are still going to be doing natural hazard studies like what I'm going to tell you about. But the technology of measuring shear wave velocities that I'm discussing here, these have many more applications. And in particular, they can help guide construction and civil engineering activities, even for structures that are not, shall we say, critical structures, such as large bridges, tall buildings, or nuclear power plants. All right. Many countries in the world, ours included, are actively rebuilding our infrastructure, our energy infrastructure in particular, for green energy. This is depending on how you count it, this is a fourth or fifth industrial revolution. All right. Similar to how in the United States, horse-drawn canal boats got replaced by nationwide by railroads using coal-fired steam in about 20 years, about 200 years ago. In green energy, you need more transmission capacity. So transmission towers, solar pedestals, wind towers, they all require geotechnical measurements. And these are going up in such numbers that it becomes impractical to do geotechnical drilling like the engineers are accustomed to. So geophysics provides a means of measuring, yes, admittedly, the very shallow subsurface, and providing guidance to the designers of the foundations of these green energy facilities, of which we need millions of them. You know, instead of one nuclear power plant, we need thousands of solar pedestals and thousands of wind towers and thousands of transmission towers. So I foresee that the need for geophysics in our countries will just increase. It will go up and up and up. Geophysical surveying will become much more widespread in service to civil engineering and construction. And thus, the early career geophysicists who we train, and it's my job to train them at the University of Nevada, they will find their jobs most likely in geotechnical geophysics. So it's our responsibility to prepare them well for this new field. So I'm going to give you just one example. One type of surface wave seismic surveys, which I call refraction microtremor, applied to one need in natural hazards and to some extent earthquake engineering, all right, which is earthquake hazard and prediction or earthquake hazard forecasting. So in a sense, what I'm going to be giving you tonight is a workflow for 3D seismic hazard. We are targeting a potential earthquake in Reno, state of Nevada, United States, and we want to ask the question, we want to be able to provide the community, the Reno community, with some answers. What will happen when the magnitude 6 earthquake hits, as it inevitably will? It must occur. Hasn't occurred yet, but it must occur. And it will occur. So we try to help the community by informing them about what can happen. Now, notice that I have put in the phrase 3D for three-dimensional. The problem is one has to use a lot of geological and geophysical information, particularly the geotechnical geophysics that I'm talking about, to be able to correctly forecast the seismic hazard from even a relatively small earthquake. So the situation is now that, and we have my student Eric Eckert and also Michelle Scalise, we have in press in the Bulletin of the Seismological Society of America, peer-reviewed, we have some really stunning observations about the potential for earthquake shaking from this relatively small earthquake in Reno. All right. And that comes, at base from shear velocity measurements. So I'm going to begin tonight by discussing shear velocity measurements with these surface wave surveys and what they show us about the Earth. I'm going to discuss a shear velocity VS database for Nevada. I'm going to talk about the parameters that one can derive from these from this database. They're known as Z1.0, Z2.5. VS30 is another one. You can, in addition to the shear velocity, you can derive these other parameters on basin thickness, these Z parameters, and those become an essential part, actually, of the 3D seismic hazard prediction. And then I'm going to fold that into a 3D model for earthquake shaking and show you these rather stunning results. So now to shear velocity measurements with surface wave surveys. What you see is the result of an early transect across the city of Los Angeles, California. This has been published in BSSA by Thelen and others, one of my students. And what is stunning about these measurements, even though they are, surface to 30-meter depth average velocities, along the closely spaced measurements, the variations are large, and the variations are extremely fine. The variations are swift and sudden, as well as large. So this degree of variation, you might say, well, this is just inaccuracy of the survey technique. And yes, that kind of, I will call it epistemic uncertainty, is in there. That is in this data set. But it also reflects the aleatory variation of velocity in the ground. And these points, although there are 200 of them spread out over a distance of 60 kilometers, those points are only 300 meters apart. And yet they show these very rapid variations in even an averaged velocity property. All right. It might remind you in the industry of a well log. And here, in fact, from the Los Angeles basin, actually quite close to this transect, is a shear velocity well log There's one close to the transect in Downey. That's the fine blue line. It's very deep, goes more than 350 meters deep. And it looks like every well log that you folks have seen, okay? There are these rapid variations due to the geology and a little bit due to the measurement technique, all right? Well, it turns out that both this horizontal transect over 60 kilometers and this vertical well log over 1/3 of a kilometer, they are both fractal curves. They show fractal variation, a geotechnical measurement of variation. All right. If you take their spatial spectra, you see the remarkable fact that they have the same approximate linear slope, which is what indicates their fractal nature. And this has been observed for natural variations in all kinds of properties, not just velocity. So we have the transect on the long range part of the spatial spectrum and the well log on the very closely spaced part of the spatial spectrum. I think it's just coincidence that they connect, but it is no coincidence that they have the same fractal dimension value. The fractal dimension is about 1.7. So that is a stunning, really a stunning and unexpected amount of variability. Now, this paper is almost 20 years old, so this is no surprise anymore. But it means that these measurements, to get an accurate reading of velocity, you cannot extrapolate, you cannot interpolate. You have to measure. All right. And so that's actually what my team and I did in Las Vegas, Nevada, USA. It's an area called Clark County, and focusing in on a map of Las Vegas Valley, which is about 50 kilometers wide, 70 kilometers wide, maybe. Each of these blue dots is the position of one Remy array. In total, on this map on the right, there are about 9,000 blue dots. Okay, this work was done over a period of 3 years. So this is a large-scale geotechnical seismic survey. All right. It cost $7 million and was funded by Clark County and the city of Henderson. That's two of the most active local municipalities for giving building permits, which is why they funded this. To get a building permit, you have to show what the velocity is, and the county decided to make the measurements themselves and contracted with my group to do that using surface wave measurement techniques. So we measured 10,000 profiles over 3 years, and all of the results are posted on this Clark County website and mapped out. And you can see the variations between, say, a more hazardous Class D soil and a slightly less hazardous Class C soil, for which different foundation designs get required. The location of the boundary is highly unpredictable. I say it's like Swiss cheese. You have to make the measurement to know where the boundary is. Okay, and if we look at the actual, this is the map that's on the county for code enforcement, and that people, design their building permits for their permit applications to meet this data set. This is the actual velocity values. So low velocities are purple and blue. Higher velocities are green and orange. And you can see that even within areas that are relatively, say, low velocity areas, there are many pockets, many randomly located pockets, apparently, of higher velocities. And within the high velocity areas, there are many randomly located pockets of much lower velocities. So velocity across a distance of only 300 meters still changes by maybe a factor of 2, in some places even a factor of 3. So the heterogeneity really rules the day. And that has a lot of impact on construction and on geological hazards. But of course, it has impact on earthquake hazards. And I'll show you the Reno implications for that. This is in Las Vegas. Of course, we can develop two-dimensional shear velocity cross sections, like you see in the middle here, from a series of surface wave surveys, and the individual dispersion images for these surveys you have grouped around here. And then uniquely in Reno, Nevada, USA, we have surface wave surveys that I call deep Remy that are not, they're more than geotechnical. They go 1 kilometer deep all the way to the basin floor in Reno. And these are published in BSSA by Poncha and others, my good colleague Asha Poncha. So these, here's a map of the western part of Reno. It's just a few kilometers wide, and it shows you our geophone locations. And then the line 1 is below the velocity cross section from it, okay, at no vertical exaggeration. And even though we are still using one-dimensional surface wave dispersion analysis techniques, we can still get very steep changes and very sudden changes in velocity. And my master's student, Jenna Graham, is currently working with me during my sabbatical so that we can try to understand, you know, how well the one-dimensional analyses are going to continue to work, and to try to understand some of the three-dimensional effects that three-dimensional variations can give to our one-dimensional data analysis. This is just a comparison between two different gravity results, not data sets, from the same profile. Again, showing a very sharp lateral variation in very deep velocity at 800 meters depth, and two different analyses of the data. One in gray, dark gray, one in light gray. They bracket where the surface wave, the deep Remy work, would place the bottom of the basin floor. Now, of course, as you know, in Mexico City, basins have a huge effect on ground shaking from earthquakes. So we will examine this in the small example of Reno. Okay, so we're on to the second item in our 3D seismic hazard workflow. That's the shear velocity, the VS database for Nevada. All right. Now you can reach it from louie.pub. Okay. And you can scroll down to VSZ profile archive. And that is shear velocity versus depth profile archive. And down in the archive, which does have its own website, which is longer. So I posted it here for you. The database has many different folders, shall we say. All right, so there are folders for Las Vegas in southern Nevada, including information on the Clark County parcel map, which is also published in a peer-reviewed paper in the Bulletin of the Seismological Society of America. And there's, let's see, here we go. There's also folders for Southern California and parts of Eastern California and elsewhere in Nevada. And then also for Reno, including the deep Remy, the deep shear velocity data that goes down to a kilometer depth. All right. And then you can extract KMLs for putting into Google Earth so that you can plot the location of the profiles that are available. And as you might expect, they are concentrated around Reno, Nevada. You can see California here. Los Angeles is down here. We have a number of measurements in Southern California. We don't have many measurements in San Francisco, in the San Francisco Bay Area, Western California. In Southern Nevada, Las Vegas, we have quite a few measurements. And many other places. Just to show you an example of what's in the database, we'll look at the San Gabriel River transect, the Stellan et al. Paper from BSSA in 2006. It's the many measurements here. You'll notice that each measurement is labeled by its shear wave velocity in meters per second. That's the number that's on each measurement. So if you want more information on each, you can use that velocity value, but if you want more information on each measurement, in Google Earth, you click on the point and you get the name of a station, the name of a measurement station. In this case, the name, which I'm sure you can't read, is 198A. And you look up in the folders, you look up the files for 198A, and there are two, okay? You look at the text file, and it gives you information about the measurement. Who made the measurement, when, what type of measurement it was. Most of these are refraction microtremor. All right. Now, for the ones that are refraction microtremor, we also give you the dispersion. We give you the dispersion image, so you can see where the data have high quality and where they do not. So, for instance, the medium low frequency dispersion curve is well constrained. The higher frequency dispersion curve above 6 Hertz for this particular measurement, 198A, is not well constrained. And you can see that on the dispersion image. All right, so we're making those all available. And the dispersion pics you can see on the dispersion image, but they're also given here in text in the file. And at the very bottom of each file, you will find the actual VSZ profile. Here, this one just has 3 layers. Okay, a simple model that fits a good amount of dispersion data. All right, so that's what's in the public database available to anyone. If you have comments about the database or ideas of what you would like to see represented in the database, and if you have ideas about how best I should offer access to the database, it's primitive access right now. I'm going to be improving it, and your thoughts are very welcome. I would very much like to hear back from you on what you would like to see there. Okay, so let's use the database now to predict basin thickness, Z1.0, Z2.5, and shear velocity, in particular VS30. All right, so just some definitions here. Z1.0 is the depth to the first occurrence of a shear velocity of, or the shallowest occurrence of a shear velocity of 1.0 kilometer per second or greater. All right, and we in this database, this comes from deep Remy surveys in Reno, and also some of the surveys we have a transect of fairly deep measurements in Las Vegas that also did yield 50 Z 1.0 values. Z2.5 is the depth to a shear velocity of 2.5 kilometers per second or more. All right. And we do have that in some places from Reno. Also in Las Vegas, though, we don't have any measurements of Z2.5. So that's going to be this all is contained, what I'm going to show you here about these measurements and predictions is in a report to the USGS, which is also on Zenodo. All right, so we extracted all measurements that have at least a Z 1.0 information. In other words, the shear velocity, the VSZ profile, showed a velocity of at least 80% of 1 kilometer per second. Because we did count, you know, if it showed 0.8 kilometers per second, considering again the aleatory plus the epistemic uncertainty of the method. All right, we considered that if we reached 800 meters per second, 0.8 kilometers per second, then that counts as a depth to Z 1.0. Likewise, if the velocity reached at least 2.0 kilometers per second, that's 80% of 2.5, and we considered that it reached Z 2.5. So we derived the Z 1.0 and Z 2.5 values that we had from the database. And then we had also in the database, we have VS30 measurements. And we made a try, and you'll see it's not very good, but we had to try to predict Z 1.0 and Z 2.5 from VS30, and also from a basin thickness that I'm going to call ZG. ZG is a basin depth estimated not by seismic techniques, but from gravity geophysics, gravity studies. And we have several in Nevada that we can work from. So the correlation between VS30 and Z 1.0 is down here, and you can see that is not a correlation. There really is no relationship in either Reno or Las Vegas. Neither is really a relationship between Z 1.0 and Z 2.5. All we know is that Z 2.5 must be greater than or equal to Z 1.0. All right, and that's really all that this is showing. So there's really no, between our shear velocity measurements, such as VS30, and the Z 1.0 and Z 2.5 parameters that the U.S. Geological Survey wants to use for earthquake hazard prediction, all right, including in Reno and Las Vegas, there's no systematic basin-wide or statewide relations. Okay, there's no correlation. All right. We know something about the statistics of the shear velocities in Las Vegas and Reno. course, in Las Vegas, we know the shear velocities very, very well, having 10,000 measurements. One thing that is pretty stunning about what you find in our database is that bedrock sites, what a geologist or an engineer, visiting the site would call definitely a rock site, a bedrock site, hard rocks at the surface, they can still have a low value of VS30. All right. So VS30 does not even distinguish bedrock sites from basin or soil sites. Okay. A lot of bedrock sites must be, at least in the Reno area, must be classed as soil sites and even soft soil sites. Again, that speaks to the difficulty of interpolation or extrapolation for shear velocities and the need to make measurements. Also, you cannot use Z1.0 to distinguish basin from bedrock sites. That doesn't work either. Z1.0 can be hundreds of meters deep for bedrock sites, as we have found many, many times around Reno, and actually in Las Vegas as well. So how do we have any idea of where we don't have a measurement? Can we make a statewide or even citywide map of Z1.0 or Z2.5? So, I mean, as you'll see, really we can't, but we have to try anyway, okay? Because the U.S. Geological Survey is going to put out a statewide and as well as citywide hazard maps, whether the information is correct or not. So we have to make our best guess. So we use the gravity-derived ZG. Okay, it's still a geophysical measurement, but gravity, and that's along the x-axis here, the horizontal axis. The vertical axis is the measured Z1.0, and this black line, that's the exponential fit that Alex Simpson found. Okay, you can see that it's not a great fit, but it is a fit, and you can get 95% confidence bounds that are these colored lines. All right, and the confidence bounds are very far apart. Basically, they're plus 50% or minus 50%. All right, but still, it's a prediction, and as long as you can accept the large uncertainty, you can use the prediction. Okay, now we could not predict Z1.0 from ZG, from gravity in Las Vegas, because there is calcite cementation at the surface that's pervasive. So for Z1.0, we only predict for the Reno area basin. We predict Z2.5 statewide. And so here are some maps for Reno. Z1.0 on the left, predicted Z2.5 on the right. And, at the basins, and there are many basins deeper than the little 1 kilometer deep Reno basin. At the basins, it's a brighter color, which means it's deeper and therefore more hazardous. And Z2.5 is everywhere at least as deep as Z 1.0. And then the predicted maps for Las Vegas on the left, and all of Nevada, and a substantial part of Eastern California. On the right, the same thing, brighter colors where there are deeper basins. And there, you know, here in Nevada, we have hundreds of basins. Okay, so we're starting to build a model now. We have velocity information, we have basin thickness information. Okay, we're ready to prepare a 3D model for earthquake shaking for Reno, Nevada, USA. All right. We're going to, it's going to benefit a lot from the deep Remy, the very deep shear velocity measurements that we've made, because we get velocities all through the sediment column, okay, all through the basin. And that's very important information. Now the building code, at least the building code used in the United States, it really only accounts for vertical resonance and also for conservation of energy of earthquake waves. All right. It doesn't do any of the three-dimensional trapping, channeling, horizontal resonance, and also the three-dimensional edge effects. All right. That's what we are going to predict with Eric Eckert's Reno shakeout scenario. All right. Which has now been peer-reviewed, and it'll be out in the Bulletin of the Seismological Society of America quite soon. Okay, just a reminder, here's a map of the Reno area, and you can see in gray the contours of basin thickness. Okay, so the deepest part of the basin is over here on the western side of Reno. There's also a South Reno basin. You can see our geotechnical VS30 measurements with the numbers and all the stations where we have them. Okay. And this basically went into constructing a community velocity model that will be available to anyone as an electronic supplement to Eckert's paper when it comes out shortly. So what results did we get? On the left, you see an animation of the seismic shaking, running pretty close to real time. Where the wave fronts are red, their magnitude is at or above 1 meter per second. Okay, these are ground velocities, ground particle velocities. Okay, now 1 meter per second is pretty extreme. Okay, and really it's these thin basins, even though they are, despite the fact that they are only 1 kilometer thick at most, okay, they still lead to extreme ground motion. And ground motions that are even above 1.5 meters per second. Okay. Now those ground motions tend to be occurring, as you can see from the PGV shake map on the right. They tend to be occurring in very small areas. You know, the really dark red is on very small areas, and they're in very difficult to predict locations. Some of the worst shaking, the highest intensity shaking, is directly over the rupture plane. That's expected, but also there's very high intensity shaking that's not near the rupture plane, like over here. Okay, and really the entire city, you know, occupying almost the whole basin, gets severe shaking that is greater than 0.4 meters per second. Okay, now we're going to compare our 3D physics-based calculation results up to a frequency of 3.1 hertz we're going to compare those against the Campbell and Bazornia ground motion model. And this is one of the ones used in the ground motion prediction equations that are in the U.S. National Seismic Hazard Model. Okay. Now, the seismic hazard model does include the Z1.0 and Z2.5 parameters, but with our less than 1 kilometer basin thicknesses, they only give about 5% amplification. So it's been ignored in our region, but we're seeing this really stunning basin amplification. Okay, so what we're going to do is compute the ratio between the 3D computed PGV prediction, physics-based prediction, that's also based on geotechnical and geological and geophysical measurements, and then this Campbell and Bazornia GMPE. Okay, so we have our 3D result divided by what I call our one-dimensional result, because it only pays attention to local, site VS30 really. And what we have then is in as it gets redder, a factor of 4 or more amplification. So this is what I would call the 3D basin amplification in Reno, due to this, really fairly small magnitude 6.3 earthquake. And you might expect an earthquake of that size, at least near Reno, every 15 years. So these, and just for some background, we did see ground motions of 2G, 2 times the force, 2 times the acceleration of gravity from a magnitude 5 earthquake. So, maybe seeing such a large ground velocity, velocities way over 1 meter per second from a magnitude 6 earthquake, maybe that shouldn't be such a surprise to us. But still, it is a surprise. And we're getting 4 times basin amplification at locations that are very difficult to predict. All right, so what we have to do is we have to start modeling additional Reno quake scenarios, because this model for the fault isn't the only one that could break. There are many other faults in Reno that could break, and so we need to do a non-ergodic view by modeling all of those. And we're getting a start on that now, modeling them up to almost 1 hertz frequency. What I want to mention is that the geotechnical variability feeds into the variability of ground motion, and that's really the main result of the study that Eckert is publishing. That the variability is unexpectedly large, and that large variability alone pushes upwards, increases the probabilistic likelihood of damaging shaking. Okay, so hopefully I have now explained to you a case for geotechnical geophysics. I've shown you how it can assist the proper consideration of earthquake hazards in a small basin, and now and suggest to you that geotechnical geophysics is going to be a very popular career for our students and our colleagues. Thank you so much. Thank you very much for your attention, and I would be honored to take any questions you have.
I'm able to read the questions on Facebook. I mean, on YouTube. There is also an option for questions on Facebook. But Daniel, one of the people who's working here with us, will give us a hand with that. One
Very
question
good.
I have is from Ivan Granados. He's a PhD student here at UNAM. He says, well, very interesting talk. Are the continuous seismic records from the deep Remy database available? And he doesn't refer to the dispersion curves.
Yeah, we're going to make them available. The deep Remy that was sponsored by the U.S. Geological Survey, which is some of it. All the data are available, but I'm going to be posting on the website and in the database, not just the velocity profiles that result, but also the dispersion curves and the dispersion images.
Same person also asked, in regions with high subsidence rates, fractures, or ground motion amplification, how does the raw database and the calculated VS models look like?
That's a very interesting question. If I go back to Las Vegas, it's the case that in Las Vegas there is fissuring, fracturing, and subsidence due to groundwater withdrawal, pumping of groundwater, as there is in many places. And that fissuring does tend, I bet that fissuring, I think that fissuring does correlate with the lower shear velocity areas. So that would be very interesting to study. So that's why it's such a good question. That's a very, I haven't thought about that, but it would be does the fissuring, does this boundary with these alluvial fans and bajadas, does that create a boundary to the fissuring as well? I don't know the answer to that question, and I would love to see that studied.
Now, there is a comment and two questions from Martin Cárdenas, one of the professors at the School of Engineering at UNAM. He says, congratulations on your next visit to Mexico and for the presentation. The method is very versatile for determining the shear velocity of materials for various purposes. I have two questions. What is the separation between receivers or array length to determine C1.0 or C2.5?
Great question. And you never know until you actually have the velocity measure, the velocity estimate, and you're trying to and you're trying to model it, the shear velocity versus depth curve from the dispersion curve. Okay, that is the final say of how long the array must be to determine velocity at a certain depth. A rough rule of thumb, as we call it here, a very rough estimate, is that you will be able to determine velocity down to half the array length. Everything else being equal, there's many factors. But that's not a bad one, and it's true almost in Reno. The deepest velocities got determined even by an array that was only 3 kilometers long. So it was there was actually coverage to greater than half of the array length. And then, once you do the analysis, there's formal ways of assessing how deep your coverage is. And there was a second question?
Yes. It says, since the method is based on ambient noise, are there any restrictions on the nature of the noise recorded, given considerations in other passive methods, such as FK or seismic interferometry?
Yes, there are restrictions. I mean, we are measuring velocity with a one-dimensional array, a linear array. So if all of the microtremor is coming from the side of the array, then we don't get an accurate measurement. What we found, and we've studied this with synthetics and real data sets, so long as at least 15% of the wave energy in the ambient microtremor field, as long as 15% of it is close to the propagating along the direction of the linear array, then it works fine. It doesn't all have to be in the direction of the array. The refraction microtremor method is effective at showing you, velocities that are too high. I mean, it can distinguish those from velocities that are correct. But you have to have a certain percentage of energy that is propagating in the right direction. So sometimes that does fail, and one has to get a correct measurement. Most practitioners, they do, they'll hammer on the ground or they'll drive a truck to put energy into the direction of the array.
Now, as I mentioned to you before your talk, several people in the engineering seismology community in Mexico actually know who you are, mostly based on this refraction, or this Remy, as the commercial stuff used to be called or is called. And could you tell us a bit about the development of Remy and the current status, in case that someone is interested in using your work, in having access to the tools that you develop, or any other Remy-related questions? It's a very broad, very general question, right, just to force you to say something.
Well, I spent the earlier part of my career doing a lot of work with land seismic, reflection records, seismic reflection records. And as you know, those reflection records can be contaminated by ground roll, which are largely Rayleigh waves and to some extent other S waves. And so I was doing a lot of work to remove the ground roll from my reflection records. And I began to wonder, can I use the ground roll data for anything? And the industry discovered this at about the same time. And now, for on-land terrestrial seismic recording, they also use the ground roll, the Rayleigh wave recordings, to make analyses of shear wave velocity. So that's how it got started, and it got commercialized by a couple of my graduates, former students, in about 2004. And that was a successful venture. But as happens to companies, they get bought up, and sometimes the companies that buy them are not very good. So what I'm doing now is, and this is part of my sabbatical, I'm thinking about all of the ways that the interpretation of Remy is uncertain or difficult. And so I'm developing and working with others on developing some new methods. They still come from, wave field transformation as applied in seismic migration, but they're new methods, and they're going to represent the dispersion curve in a different way. And I think you'll find that when I show it to you, I may have some examples at the time of my visit, and certainly later I will. When I show it to you, I think you'll find that this new representation is a lot more intuitive and a lot easier to interpret and model. So there's going to be a new venture. I am, of course, as always, I'm still an academic, and I'm looking for collaborations. I can right now, if I collaborate with you, then I can do a Remy or a new style analysis of your surface wave data, and we can collaborate on the results. And I'm expecting in about 6 months that we'll have a new software package available that will contain these new ideas and be the new analysis method. Really the successor to Remy. Now, there's a lot of things have to happen before that's a reality, but and I would like to see, especially when I visit, I'd appreciate talking with anybody who's interested in this, either in a research collaboration or in a commercial collaboration, and because I want this method to be used and available to everyone.
Okay, there is one more question from Martin Cárdenas. He says, in your studies, what was the frequency of the geophones? And can you tell us something about your instrumentation?
Yeah, even for the deep Remy studies in Reno, they were geophones that had a principal frequency of 4.5 hertz. And given the length of the array and the long recording times, so we would typically record for at least 4 hours. And we would split them out into records that were individually at least 2 minutes long. So those records, we can see, we can pick the dispersion curve at less than 1 hertz. Plenty of examples of dispersion data, and it's Pancha shows it in her 2017 paper on Reno Deep Remy, down at 0.5 hertz, 2 seconds period. There's good dispersion data, and that was enough to get into the basement, get velocity measurements into the basement in Reno.
Are there any questions from Facebook? ¿Hay preguntas en Facebook? Daniel? No? Okay. Then if there are no more questions, I think Gerardo has something to tell you about before we finish.
Well, thank you all very much. Very good questions.
Thank you.
Thank you very much, Louie. We are going to give you recognizing is I would say in Spanish for the people, they say the Asociación Mexicana de Geofísicos de Exploración otorga el presente reconocimiento al Dr. John N. Louie por su conferencia Surface Waves Surveys Building a Community Seismic Velocity Model for Nevada, USA, for a physics-based 3D earthquake ground motion prediction. I would like to thank on behalf of the Mexican Association of Geophysicists of Exploration Geophysicists for this presentation. It is a subject very out of the common subjects we treat or we used to treat. We are trying to spread our knowledge on all the branch of geophysicists. It can be done. I thanks to Sergio to contact us with you, and I hope it's not the last time you give a talk to us. It's a great presentation. Thank you very much.
Thank you so much.
Bien, a nombre de la Asociación Mexicana, agradezco a todos los que estuvieron conectados y les pido de favor que hagan extensivas estas presentaciones que son de gran interés de divulgación científica. Muchas gracias a todos y buenas tardes.
Bye bye.